Thank you. The atmosphere can refract or bend radio waves. They don't actually reflect off like glass. They actually refract uh, and bend through the ionosphere, which is fairly thick. And the ionosphere is the upper layer of the Earth's atmosphere composed of oxygen and nitrogen. And that's the first thing that the solar radiation hits. So you've got ultraviolet and X-rays and other things that are high energy, and they're ionizing those uh, oxygen and nitrogen atoms and any other impurities there. I don't think carbon dioxide gets up that high. And that's why it's called the ionosphere. It ionizes that layer. So you've got uh, atoms missing electrons because you had enough energy to free the electrons. So they're floating around as negative ions, and you got positive ions. And that electric field that's created because of those dipoles is what refracts or bends the radio waves. And it's different in the daytime and the nighttime, obviously, because at night you don't have that solar radiation hitting it on the dark side, but it still retains a lot of the ionization. So it doesn't refract as much, where it's more in the daytime. And in the daytime, the uh, ultra uh, the UV and other things can penetrate farther down into the atmosphere. So they can even get down into what we call the D layer. Is divided up into D, E, and F. And F is split into F1 and F2 in the daytime, merges into F at nighttime. So they different layers react differently at different times of the day, and frequency and the angle that it's going, kind of like light reflected off of glass. There's a critical angle where it will reflect, and if it's less than that angle, it's going to go through the glass. That's the way the ionosphere works. So it has to be below the critical angle, and it has, a bunch of conditions before it will refract, and we'll get into some of that. In the case of UHF, and VHF, which you mostly be using as a technician, those are line of sight signals. So they don't get refracted through the ionosphere. So you'll be talking line of sight to a repeater or another person with a handy-talkie. And that means that the curvature of the Earth is what's blocking your line of sight. So there's a formula that how far you can go line of sight where you see the horizon is 1.23 times the square root of your height in feet. So if you're tall and your radio is 6 feet up off the ground, then the square root of 6 times 1.23 is how far that signal is going to go before it's blocked by the horizon. So another person with the same height and the same radio can be that far away on the other side of the horizon. So that's the limit of how far you can go. Except, especially on VHF.
So you said their radio signal has to be able to reach your radio signal. You don't actually have to be able to see each other.
Well, technically you do, because
each other.
if you had a telescope, you'd have to be able to see them. In other words, if they're down too far over the horizon, you're going to hit the Earth.
Signal, you're here, and the signal.
But it's straight.
Your signal.
No, it's straight line.
Okay.
Yeah. I mean, your signal's doing that, but the only part that gets over to him is the straight line part. Anything at an angle is going over it. So it's only
Well,
only line of sight.
exaggerating the point, because if you're on the curvature of the Earth and he's slightly past it, there's a little angle there. You should reach that point in the middle.
No, but it doesn't work that way.
Okay, just asking.
However, there is, because of some other effects, there's some slight bending because of the radio wave can kind of follow the curvature a little bit. So it actually turns out you can get 1 over the square root of 2 times the square root of the height. So it's like 15% farther. So instead of whatever that, and I can't do the square root of 6 in my head, whatever that would be, you can get about 50% farther on both sides, because you both have a little over the horizon, they call it. And that's the difference in line of sight and the radio horizon, which allows you to go slightly over the horizon, you get a little bit farther. So it's the height of the two in the formula. So if one of them's a repeater, like our repeater on the VAB at 525 feet, okay, line of sight to that is probably 40, 50 miles. And depending on where you are, I mean, you can do another few miles, 7 miles away. But it's strictly line of sight with a small amount of curvature. And I think you get more curvature at VHF than you do at UHF. And Ernie's not here, he could confirm that. Oh, this is just showing how the formula is derived. And here you got distance 1 and distance 2, which depend on the height of these two people. But you can't, well,
That's what I was picturing in my head, except the antennas are a little bit shorter. Would it still reach? And I guess not, based on that picture.
now if you raise the antenna, you get further.
Right.
But you're normally limited more line of sight than power. So why is the radio horizon for VHF and UF signals more distant than the visual horizon? In other words, why can you go farther than you can see?
Charlie?
They use that big term refraction. My ophthalmologist uses that too, and they charge you about $100 for a refraction test. Why are simplex UHF signals rarely heard beyond their radio horizon? Charlie?
Yeah, they can't bounce off the ionosphere.
Right. And it says simplex, which means there's no repeater involved.
Which is why I went with 2 week.
Well, you could be too weak, but usually has to do with line of sight. And you don't get propagation, or you get very little propagation. Also has to do with polarization, which we're not up to yet. There's things called multipath, where signals can bounce or refract off of other things, like buildings, for instance. So if you're actually line of sight, you know, there's buildings and trees and things in the way. So they can actually reflect or bend your radio wave. We'll talk about, is it on here? Knife edge and a few things like that, which can come into effect. But the bottom line for multipath is because it's possible to have more than one path from point A to point B, the signals can arrive at different times because of the path length not being the same. Because you might go direct, you might have reflection off of a building over here, it's still line of sight, okay, but it's going this way, so it's longer path, so it gets there later. So it's kind of like an echo. And depending on how it gets there, it could be in phase or out of phase. So it could either add to the signal or subtract from it. And because it's not consistent, you can get a fluttering sound where it'll get larger and smaller, all those kind of effects. And just by moving a few feet, you can change that path enough that it might make it better or worse. And it can have and more than just two, especially if you're in a city with a lot of buildings. I mean, you can have bounces all over the place. And if you're driving around in a car, and you've got multipath coming, and it's going to change as you move. And one of the things, the result of that is called picket fencing, where as you're driving along, you're going to have the signal loud, soft, loud, and it's kind of like stick on a picket fence as you went by on your bicycle. In the case of digital, it behaves differently than analog, where you don't have loud and weak signals. You either have a signal or you don't have a signal. Digital is either a nice signal or no signal. You might get some garbage, but it behaves differently than an analog signal.
Hey Bob, I have a question about digital just real quick. And so if I'm at my house and I have a digital transceiver that I hook up to my internet,
Yep.
does that cancel out me needing a big antenna? Since it's going through the internet, or?
Well, it depends on what you want to do. If you're talking about something like, let's say, D-Star or MR, and you got a hotspot that's connected to the internet, that's connected to other repeaters and hotspots through the internet all over the world, and they have these things called reflectors. In the case of D-Star, they call them talk groups. In the case of DMR, so you can link to one of these and along with other people around the world, and only those people on that particular reflector are seeing the signals back and forth, and you can talk to people like reflector 1 Charlie on D-Star is worldwide, and I can, with my hotspot, I can talk to people in England, South Korea all the time. They're hard to understand, especially the English. It sounds like they had a few pints. I don't know what part of England they're from, but yeah, I mean, if that's what you want to do and it's easy, all it requires is a digital radio, which will cost more than a Baofeng.
Right.
But hotspots are cheap. You can put one together yourself for like $30. You can buy one for a couple hundred. So if you're lucky enough to have a repeater for D-Star or DMR or Fusion, then you won't need the hotspot. Unfortunately, we're not close enough to have a DMR or well, I think there might be a DMR repeater. Okay. But there's no, the closest D-Star repeater is 40 something miles away.
Okay.
And there's lots of different reflectors and talk groups. So, there's one for this local area. There's a East Coast reflector. There's the worldwide one. And then there's ways, which I haven't done, to connect to other modes like we talked about earlier, where I can go from D-Star to DMR and things like that.
Watch the video on this and not take up too much time, but I heard you could your own little talk group.
Oh, yeah. Yeah.
Make your own little, like,
Yeah.
you can join somebody.
I think you just have to register it.
Create your own little talk group and just talk
Right.
privately between.
Of course, other people have to know what it is.
Yeah. You can just provide that information and you can.
Right.
Other people can talk to you.
Right. And you switch talk groups just by unlinking and linking to a different talk group.
Thank you.
Why do VHF signal strengths sometimes vary greatly when the antenna is moved only a few feet?
C.
Very good. What is the meaning of picket fencing?
You just said that.
Bravo.
Flutter, yeah.
What effect does multipath propagation have on data transmissions?
D.
Yeah.
Right. At a high error rate, you don't hear anything. Okay, repeater access. Normally it's a direct path, although you can have reflections off of things to get to a repeater. One of the examples is repeater on the other side of the mountain. Doesn't necessarily apply to us because we don't have any mountains, but it's not line of sight. One way to get there is a thing called knife edge diffraction, which is the way light works. Light will bend around a sharp edge. Radio waves are light waves at a different frequency. They will bend around a sharp edge. So in some cases, the top of a mountain is enough of a sharp edge where you can bend the radio wave over the mountain
It's how
or over a building.
stealth bombers work. That's why there's all sharp edges.
Or around a building. On the edge of a building, it will occur. So that's one of the ways to get farther or get around an obstruction. So there are indirect paths where you can do that bouncing or reflection. Another problem in the particular UHF and up is water absorption. So anything containing water, people, trees, fog, rain, absorbs high frequency radio waves. So UHF doesn't work good in the rain. And a room full of people will absorb a lot of it too. We don't think of ourselves as a bag of water, but we are. This is an example showing, in this case, repeater is up really high, so I can get to somebody over here in the valley, with that repeater. I thought I had one showing this as like doing a knife edge on something like that too. I've never been able to do that. I've never transmitted where there's mountains. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the line of sight?
B.
Very good. Oh, this one's got knife edge. Of course, you don't normally see mountains quite that sharp either. I didn't draw it. But it actually bends it so you've got this region over here that's now accessible. So you can get to this repeater. Which could be quite farther than you normally could on straight line of sight. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
Edge diffraction.
What is the effect of vegetation on VHF and UHF?
Absorption.
Bravo.
well, VHF and microwave, but that includes UHF.
We are bags of water.
Yes. Polarization. I said we'd talk about that. Polarization is the orientation of the electric field portion of the wave. And its orientation with respect to Earth. So if I've got a horizontal antenna, like shown, horizontal dipole, which is kind of the simplest form, and that radio wave is propagating out perpendicular to the element, and the electric field, okay, is aligned with that antenna element. It's going back and forth across it. The voltages and the currents are traveling back and forth across the dipole. That wave is parallel to the Earth. We call that horizontal polarization. If I rotated that antenna 90 degrees, so it's now vertical, okay, that E wave is now radiating the same way relative to the antenna, but it's now vertical relative to the Earth. So that would be vertical polarization. Your handy-talkie with its little whip antenna is vertically polarized. If you're talking to a repeater, it's normally going to have a vertical antenna. It's easier to do that way. Plus, the radiation pattern for a vertical antenna is a big horizontal donut. That's why AM radio towers are vertical antennas, because it gives them a broad radiation pattern. Right. If we're doing line of sight, you need to have the same polarization, which is on a handy-talkie. I mean, you're kind of fixed. You need to hold your handy-talkie so it's vertical, because if you're talking to a repeater, it's almost guaranteed to be vertical. If I rotate that handy-talkie 90 degrees, I may not even be able to contact the repeater because I'm cross-polarized. So the intersection of those signals is very small, whereas when they're in the same polarization, I get what's called the aperture, okay, which is much larger this way. And when I cross the aperture, there's very small intersection. So I get a very reduced signal. In the case of, and hopefully Dan knows more about long distance VHF, UHF, but if you're horizontally polarized, use a horizontal antenna, you can get some propagation long distance on VHF and UHF, from my understanding. I have not done it.
Well, once it comes in contact with the atmosphere, doesn't it become elliptically polarized?
If it's refracted from the ionosphere, it's becomes elliptically polarized. I don't know if this is refraction or just I don't know enough about doing horizontal with VHF and UHF. But in the case of repeaters on those, you're going to be vertical for it to work. This is showing our standard wave again, which is either horizontal or vertical, depending on whether you rotate it 90 degrees. This is what it looks like if it's circularly polarized, which is actually a special case of elliptically polarized. In the case of circularly polarized, it means that the two out of phase are equal. So it will do a circle. If I've got a higher signal in one direction than in the other, depending on the phasing, okay, then it will be elliptical. It won't do a perfect circle because the radii are different. So it becomes an ellipse. And that's what happens, and I don't understand why. You don't need to know why, but when you get refraction off of the ionosphere, regardless of whether you started off vertical or horizontal, it's going to become elliptically polarized as it's refracted. So in the case of long distance propagation, it doesn't matter whether you have a horizontal or vertical antenna. The only time it matters is in line of sight, essentially, or like with a space station or satellite. And there you have a different effect. It's Faraday rotation because those are usually rotating. Okay, so their antennas are going from horizontal to vertical and back. So they're actually mechanically rotating the signal as opposed to doing it by different phases. And that makes it harder to track and communicate with a satellite because you've got, and usually what people do is they'll have a cross polarized antenna where it'll basically be a horizontal and a vertical. So it can receive as that signal rotates. And then you have to also at the same time compensate for Doppler shift because it's moving. So the apparent frequency changes as it's coming towards you and going away from you. And it takes like 3 hands to do a satellite thing with a handheld antenna. A lot of people do it, are successful. You can do it with a handy talkie. I have a friend of a friend that's moved out to, I think it's Utah. And out there in the middle of Utah, he does it frequently when a satellite or space station goes over. He gets out of his truck. What property of a radio wave defines its polarization? Actually, I think they left off. It's really should be the orientation of the electric field with respect to Earth. It's got to be referenced to something. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization?
Signal strength is reduced.
Right. What antenna polarization is normally used for long distance continuous wave, that's Morse code, and single sideband, which is a form of AM, on the VHF and UHF bands?
Charlie.
One of the reasons they don't use vertical is it's harder to do a beam antenna vertically than it is horizontally. So we learned about line of sight and what the 2 formulas are, and the radio horizon is the square root of 2 times the square root of the height as opposed to 1.23. So you get about, I think that comes out about 15% more distance. Multipath, you get signals arriving by multiple paths that can be in phase or out of phase. So they'll add or subtract, they can change. So you get fluttering, you get picket fencing, particularly in, well, you almost have to have a car moving to do picket fencing. You can get high error rates if it's a data or digital transmission, digital voice, or any of the data modes. Reflections off of buildings can get you around things. Knife edge diffraction can get you around or over. Water absorbs UHF and microwave. You have horizontal and vertical polarization in addition to elliptical. So easy things to